In this short video, we're going to extend our Lewis dot structure theory away from ionic compounds now to look at covalent compounds. Whereas ionic compounds are looking at exchange of valence electrons, covalent compounds are looking at sharing of covalent electrons. Let's consider mixing nonmetals. So I should mention that covalent is exclusively nonmetals. So nonmetals only. So let's look at hydrogen. We know that hydrogen, although it's not really a group 1 metal, it is lumped in the periodic table by group 1. So we know that it has one valence electron. It also has a box because it's a non-metal. So that means it has an electron to share. It can also receive an electron. So if we have two hydrogens come together, they can interact. Now, rather than forming an ion, then we have two dots. Now each dot is in a box. So we originally had two valence electrons and we had two boxes. We come together, we still have two valence electrons and two boxes. But one electron and one box belongs to one hydrogen, and one box and one electron belongs to the other hydrogen. So we know that each hydrogen has access to two electrons. The hydrogen on the left has access to two, the hydrogen on the right has access to two. We can just draw this as either H2, or we can draw it as H line H, where the line represents the bond, or the line represents two electrons. We see here we have, well, you wouldn't really talk about definite proportions here because there's only one type of element. You really talk about definite proportions when you have at least two types of element. So let's try that with hydrogen and oxygen. Hydrogen, as above, has a dot and a box. Oxygen, as we've seen earlier, has 6 dots and 2 boxes. So let's draw those in. 6 dots and 2 boxes. Now, I've only got one valence electron on hydrogen, but oxygen requires 2. So I'm going to have to multiply my hydrogen by a factor of 2 because I need to fill oxygen with 2 valence electrons. So I would write oxygen. So I've got my 2 hydrogens, so I've got 1, 2, I've got 1 oxygen, just 1. Let's put some dots in here. So I've got, the hydrogen has a dot in a box. The hydrogen has a dot in a box. The oxygen has 6 dots. And 2 boxes. So we have a conservation of dots and boxes. So I should have 2 dots and 2 boxes plus 2 more boxes and 6 dots. So I should have 6 dots plus these 2 is 8 dots total. And there they are. I should also have 2 boxes from over here and then 2 boxes from over here. So I have 4 boxes. As before, I can write dots between atoms as a bond. So I could write this as H bond O bond H. Now these dots that don't have an atom associated with them, they're called lone pair electrons. So I would just write those as dots. So the dots that are between atoms are called bonding pair electrons, and they form a bond, a covalent bond. The electrons that don't have an element associated with them are lone pair electrons, and we write those as dots. So here we can clearly see we have a 2-to-1 Joseph-Proust's definite proportion. And again, it's appropriate to look at definite proportions here because I have more than one type of atom. Okay? And finally, let's look at carbon and oxygen. So I'm going to draw a carbon like up here. So I have carbon here with its 4 dots and its 4 boxes. And I have oxygen like over here with its 6 dots and its 2 boxes. Well, carbon has to fill 4 boxes and it can also give 4 dots. Oxygen has to fill 2 boxes and it can potentially give 6 dots. So with a little bit of practice and trial and error, you will see that you have carbon, oxygen, oxygen, dot, 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 dot. So we actually have 4 valence electrons between each carbon and oxygen in this structure. So let's look at the dots first. Well, first of all, I notice that I've got 2 boxes, but I've got 4 dots. So I clearly need to scale oxygen by 2. This gives me 4 dots here and now 4 boxes. So that's why I have 2 oxygens here, because I've scaled by 2. So how many dots do I have total? Well, I've got 6 original dots, but I've scaled by 2, that's 12. And then I've got 4 from over here, so that's 16 dots total. So I've got 2, 4, 6, 8, 10, 12, 14, 16. So there's my 16 dots accounted for. But I've also got 2 multiplied by 2 boxes, that's 4 boxes, plus my original 4 boxes, so I should have 8 boxes. And here they are. So you'll notice that the bonds between atoms are typically the way I've drawn it here, they're always in boxes. And the electrons that are not between atoms are not in boxes. So I've got my 16 electrons on both sides, my 16 dots, my 8 boxes on both sides, but I'm left with this double bonding. So I could write CO2 in a 1-to-2 Joseph-Proust definite proportion, or I could just write C double bond O with my 2 lone pairs or 4 lone electrons on my oxygen. So you can probably see that for covalent compounds we have nonmetals only. For nonmetals we have dots and boxes. Typically the boxes go between atoms and are filled. Any extra dots go on, well here I've shown them on oxygen. We'll talk about, that would be another video. We look at ionization energy and electronegativity, but that would be beyond this video. And one thing to notice here is that for every dot you have, that's how many bonds you want to form. So for every dot you have, and here I have one, I want to form one bond, so I form one bond. Carbon has 4 dots, so carbon wants to form 4 bonds. 1, 2, 3, 4. Oxygen has 2 boxes in this case, so it forms 2 bonds. 1, 2. So again, to repeat, and probably more consistently, for every box that you have, so not necessarily dot, but for every box that you have, that's how many bonds you form. So 1 box, 1 bond. 2 boxes, 2 bonds. 4 boxes, 4 bonds. 1 James Bond. And that was a joke.